Hello everyone, welcome to the new chapter, all about complex numbers. So you've seen this statement before, x squared plus 1 equals 0 has no solutions, and that's because we're going to have x squared equals minus 1, and there's no real numbers if we multiply together that equal a negative number. But I got some news for you. We lied. Okay, so the actual full statement for that is there's no real number solution. Okay, and for a problem as complex as this, mathematicians had to use their imagination. Okay, I'll get my coat. What mathematicians have done is they've created this new number called I, which is equal to the square root of minus 1. And you can see in this situation here, if I had the square root of minus b, b is an element of the real numbers, then just some typical square root manipulations. So separating out the factors, we end up with square root of b times the square root of minus 1, and we still leave the square root of b, and the square root of minus 1 is this plus or minus I. And if I was to substitute in, say, 4 for b here, then we would end up with the square root of 4 being 2 plus or minus 2i. Okay? And what a complex number is when we start combining real numbers and these square roots of negative 1. Okay? And so we've got a real number plus a real coefficient of this square root of negative 1. And our conventions that you're going to be using are, instead of using x, which we tend to use for the real numbers, you'll see that z is the most common name for a variable in complex numbers. Also, when you have a complex number z, if the coefficient for the complex component is 0, so in this case if b is equal to 0, then you've just got a plus 0i, which is a, and that's just an element of the real numbers. Similarly, if a was 0, then we've just got z equals bi, and that's what we call an imaginary number. Now, because making b gives us a real number, that shows you that the real numbers are a subset of the complex numbers. And if we go back to our old-fashioned number sets diagram that we saw earlier on this year, we've got our counting numbers, which are a subset of the integers, so just adding the negatives and 0. Then we put fractions in between the integers, and then we found that most numbers actually can't be represented as fractions, and that gives us the real number line. Well, the real number line is inside the set of complex numbers. Okay. And following on from what we said earlier, for z equals a plus bi, instead of saying b is equal to 0, you can just use this real of z. And instead of saying a is equal to 0, you could just say this imaginary of z. It's really important that you understand that the real component and the imaginary component are going to need to be treated differently in arithmetic. And you're going to see why as the chapter progresses. So because we need to treat them differently, if we have these two real numbers, a plus bi and c plus di, so they're different real coefficients there, then the only way that they're equal is if the real component, a and c, are equal to each other, and the coefficient for the imaginary numbers, b and d, are also equal to each other. So the first bit of work you're going to have to do is work through that. I've got two examples for you here. The first one is saying, if I have this complex number 4 minus 3i, and it's equal to this other complex number, but we're not representing everything in numbers there, we've got 2a plus bi. What's a and what's b? Right, so this one is really straightforward. So the two real components, 4 and 2a, have to be equal, don't they? So we've got 4 equals 2a. And dividing both sides by 2 is really simple. A is equal to 2. And we also have over here, let me change colors, the imaginary components. So bi is equal to minus 3i. So that means that b is equal to minus 3, and there's no steps I need to do there. We know that a is equal to 2 and b is equal to minus 3. It's not too challenging, is it? Let's have a look at the next example, which is a little bit more challenging, but I think you'll be fine. We've got this complex number here represented in a slightly more complex way, as I said, but this is still the real component. And we got the real component over here. And this part here is still the coefficient for the imaginary part. Okay, so 2a plus 3b has to equal minus 1. And a minus 2b has to equal 3. And from here, it's a simple simultaneous equation problem. If you just multiply the bottom one by 2 and subtract it away from the top one, you'll be left with 7b is equal to minus 7, and therefore b is equal to minus 1. And substituting that in, 2 minus 3 is equal to minus 1 means that a is equal to 1. All right, so that's all there is to do there for example 1 and 2. Please get on and have a crack at question 2 in your textbook, and I'll see you in the next bit after that.